Good morning. Today we'll start with vapor and combined power cycles. The Carnot vapor cycle. We'll start with this because this from Carnot, then we will go to the Rankine cycle. So we have mentioned repeatedly that Carnot is the most efficient cycle operating between two specified temperature limits. Thus, it is natural to look at Carnot cycle first as perfectly ideal gas cycle for vapor power plants. If we could, would certainly adopt it as ideal cycle as explained below. However, the Carnot cycle is not a suitable model for power cycles. Throughout the discussions, we assume steam to be the working fluid since it is a working fluid predominantly used in vapor power cycle. Consider a steady flow Carnot cycle executed within the saturated dome of pure substance. The fluid is heated reversibly and isothermally in a boiler and expanded isotropically in a turbine, condensed reversibly and isothermally in a condenser, and compressed isotropic by a compressor to the initial state. So these are the four processes here. So you can fit a Carnot cycle in TSS diagram within the dome. So 4 to 1 is your compression, 1 to 2 is your heat addition, 2 to 3 is your expansion, and 3 to 4 is your condensation process, heat rejection. So isothermally heat transfer to or from a two-phase system is not difficult to achieve in practice since maintaining a constant pressure in the device automatically fits the temperature at the saturation value. Means if you transfer from heat from 1 to 2, you will convert the liquid into vapor. This is possible if you fix the pressure, automatically the temperature will be fixed and the phase will change from liquid to vapor. But limiting the maximum temperature in the cycle also limits the thermal efficiency because in case of water, if you take water as a working fluid, this is a critical point which is 374. So you can't go beyond this point, means you have to be below this point. In the two-phase region, you can't go beyond this point, otherwise you have to, there will be a single phase. So any attempt to raise the maximum temperature in cycle involves heat transfer to the working fluid in a single phase, which is not easy to accomplish isothermally. The isotropic process 2 to 3 can be approximated closely by a well-designed turbine. However, the quality of steam decreases during this process as shown on the TS diagram in figure. So you can see when you will expand from 2 to 3. So during expansion at 2 you had the pure vapor, but during expansion when you go to the 3, so you had some part of the liquid, you can see in the form of liquid. So the liquid will strike with the turbine blades and it can harm the blades. So the impingement of liquid droplets on turbine blades causes erosion and is a major source of wear. Thus the in steam with qualities less than about 90% cannot be tolerated in this operation of power plants. Means that 3 points should be such that the dryness fraction should be 90.9 or 90% should be the steam. 10% amount of water can be tolerated in the power plants. This problem could be eliminated by using a working fluid with a very steep saturated vapor line, or you can, instead of water, you can use a fluid whose this vapor line is very steep. Means this curve should be like this, so that the 3 point will remain to the near to the liquid vapor line. The isotropic compression process, which is 4 to 1, involves the compression of liquid vapor mixture to a saturated liquid. There are two difficulties associated with this process. Means after 3 to 4 is your heat rejection, and at 4 you have to compress the two-phase mixture. Means liquid and as well as vapor you have to compress, and there is no actual device which can compress two-phase liquid. So first is, it is not easy to control the condensation process so precisely as to end up with the desired quality at state 4. Second, it is not practical to design a compressor that handles two processes. The first difficulty is during 3 to 4, which is your condensation process. So at the end of condensation process, so it is difficult to control the quality of the steam. You can either do the complete condensation, means you can go up to at this point, you can fully condense the steam, but it is not possible to store the quality of a steam during condensation. Means it is difficult to achieve 4 point, and second, there is no device which can raise the pressure of two-phase system. It is impractical. So some of these problems could be eliminated by executing a Carnot cycle in a different way. Let's discuss the Rankine cycle, the ideal cycle for vapor power cycle. Means a little modification is done in Carnot cycle. So what are these modifications? if instead of 0.4 you will condense the steam fully up to this point, which is your saturated liquid. So this is your first modification done. Now the steam inlet steam is fully condensed to liquid, and this liquid is again pumped with the help of a pump, or you can say pressure of this liquid raised with the help of a pump from 1 to 2. So this is possible, and also pump valve will increase. Second modification is at 0.3. So this point, which is this point here, instead of using just saturated vapor, you can superheat the steam at constant pressure, and after superheating, this would be the, you can say, you will get into the superheated region, and when you expand from superheated region, definitely you will end up with high dryness fraction of steam, means near to the vapor line. So when you end up at 3, so if you you can say this is the turbine inlet 3 point, which is superheated steam. So when you expand from 3 to 4, you will end up in you can say near to the vapor line, means the quality of steam at the turbine exhaust can be controlled, and you can avoid the erosion and you can say damage to the turbine also. And this constant temperature heat addition is replaced by constant pressure heat addition. So 2 to 3 is your heat addition at constant pressure. So with this modification, this cycle is called, on TS diagram is called a Rankine cycle. So as you can see, from 1 to 2 we are using pump here, from 1 to 2. 2 to 3 is your boiler, which is heat addition in boiler at constant pressure. 3 to 4 is your turbine work, and 4 to 1 in the condenser, this liquid vapor mixture is condensed fully to the liquid state at a constant temperature and constant pressure in the condenser. Now these 4 processes here are combined here. 1 to 2 is your isentropic compression is pump. 2 to 3 is constant pressure heat addition in boiler. 3 to 4 is isentropic expansion in a turbine, and 4 to 1 constant pressure heat rejection in condenser. So in a Rankine cycle, water enters the pump at state 1 as saturated liquid and is compressed isentropically to operating pressure of the boiler. The water temperature increases somewhat during the isentropic compression process due to a slight decrease in specific volume of water. The vertical distance between 1 and 2 on TS diagram is greatly exaggerated for clarity. If water were truly incompressible, would there be a temperature change at all during the process? Water enters the boiler as a compressed liquid at a state 2 and leaves as a superheated vapor at state 3. The boiler is basically a large heat exchanger where the heat originating from combustion gases, nuclear reactor or other sources transferred to the water essentially at constant pressure. The boiler together with the section where the steam is superheated is often called steam generator. The superheated vapor at state 3 enters the turbine where it expands isentropically and produces work by rotating the shaft connected to an electric generator. The pressure and temperature of steam drop during this process to the values at a 4 where steam enters the condenser. At this state, steam is usually a saturated liquid vapor mixture with high quality. Steam is condensed at constant pressure in the condenser, which is basically a large heat exchanger, by rejecting the heat to cooling mediums such as lake, river or atmosphere. So steam leaves the condenser as a saturated liquid and enters into the pump, completing the whole cycle. Energy analysis of either Rankine cycle. All 4 composites associated with the Rankine cycle, pump, boiler, turbine, condenser, are steady flow devices, and thus for all 4 processes that make up Rankine cycle can be analyzed as steady flow processes. The kinetic potential energy changes of steam are usually small relative to the work and heat transfer terms and are therefore usually injected. Then the steady flow energy equation is the Q in minus Q out plus work in minus work out is equal to enthalpy at exhaust minus enthalpy at inlet. So as we know, the pump, in case of pump there is no heat transfer. So in case of pump you can express work pump is equal to H2 minus H1, means enthalpy at the pump outlet minus enthalpy at the pump inlet, or work pump is equal to expresses V into P2 minus P1, where V is the volume of fluid at 1, or H1 is the enthalpy of the fluid at 0.1 at P1 pressure. Boiler, in case of boiler, work is 0. In case of boiler, only heat transfer device. So in case of boiler, W is 0. So Qin is equal to H3 minus H2, which is enthalpy of the fluid stream at outlet of the boiler, and this H2 is enthalpy of steam at the inlet of the boiler. Turbine, which is again it is work producing device, no heat transfer, adiabatic expansion, we ideally assume. So work of turbine is equal to H3 minus H4, enthalpy at inlet of turbine minus enthalpy at the outlet of turbine. This is the net amount of work output by turbine. Condenser, again during the condenser there is no work, so heat out in the condenser is H4 minus H1. The thermal efficiency of a Rankine cycle is determined from, so efficiency is always net work output divided by desired effect, which is net work output, which is difference of turbine work and compressor work, means turbine work minus compressor work. This is net work output divided by heat supplied, or it is 1 minus Q out by Q in. So the conversion efficiency of power plant in United States is often expressed in terms of heat rate, which is the amount of heat supplied in BTU to generate 1 kilowatt electricity. The smaller the heat rate, the greater the efficiency. Considering 1 kilowatt is equal to 3412 BTU, and disregarding the losses associated with the conservation of shaft power to electric power, efficiency thermal is defined as 3412 by heat rate. Now suppose in case of power plant, suppose heat rate is 11,363. So if you put value here, you will get equivalent efficiency 30%. It means the thermal efficiency can also be interpreted as a ratio of area enclosed by cycle on TS diagram to area under the heat addition process. The use of this relation is given in the example. So deviation of actual vapor power cycle from ideal as 1. The actual vapor power cycle different from ideal Rankine cycle as a result of irreversibilities in various components. Fluid friction and heat loss to surrounding are the two common sources of irreversibilities. So you can see here, first of all, this 1, 2s, 3 and 4 is your ideal cycle, but as we know, the compression is not isentropic, so it will deviate from isentropic, and this 2a is your exit condition of the fluid at the compressor outlet, and during expansion from 3 to 4s it also is not isentropic, so actual process is 3 to 4a, it deviates from isentropic process. And further there are losses, pressure drop losses in the boiler, because boiler having pipings and there is a pressure drop during the when your steam flow from the boiler, so this much amount of pressure drop will occur. So this actual cycle is dotted line, and you will end up at point 3, and you have to overcome this pressure drop. Pump has to do more amount of work. So next is 3 to 4 means during a turbine, and at 4 usually we end up in superheated region, because we don't want any vapor or liquid form, you can say water, to impinge on turbine blades. And from 4 this superheated steam is condensed in the condenser, and even during condenser there is a little bit pressure drop here. So this dotted line represents the from here to here, this is your pressure drop in the condenser. So irreversibility in the pump, pressure drop in the boiler, irreversibility in the turbine, and pressure drop in the condenser are the 4, you can say, irreversibilities and losses in the actual Rankine cycle, which we have to include. So same is compiled here. Fluid friction causes a pressure drop in boiler, condenser, and the piping with various components. As a result, steam leaves boiler at a somewhat lower pressure. Also the pressure at the turbine inlet is somewhat lower than that boiler exit due to pressure drop in the connecting pipes. The pressure drop in condenser is usually very small. To compensate for these pressure drops, the water must be pumped to a sufficiently higher temperature pressure than the ideal cycle calls for. This requires a larger pump and larger work input to the pump. The other major source of irreversibility is heat loss from the steam to the surrounding as steam flows through the various components. To maintain the same level of net work output, more heat needs to be transferred to the steam in the boiler to compensate for these undesired losses. So these losses, efficiency of pump and efficiency of turbine is compiled here. So in actual condensers, for example, the liquid is usually subcooled to prevent onset of cavitation. The rapid vaporization and condensation of the fluid at low pressure side of the pump impeller, which may damage it, means apart from the condensation up to this here, we will actually subcool the liquid and we will go into the liquid region to avoid any cavitation in the at the you can pump blades. So this is up to here the actual Rankine cycle. Like this channel, subscribe it, and thank you for watching this video.